All right. So before I continue with fault tolerance, which of course is a very interesting and important topic, I want to mention some things about the project. I was chatting a little bit before the class with people that are present, but for the kind of the record. So the last project is split into two parts. So it's really two projects, right? The first part is a more normal part, and the second part is more interesting, right? And it's very open-ended. Now, intentionally, I left the first part to be simpler, so you can start working on the second part early on, so you can actually accomplish something interesting by the time it's due, which is the end of the exam period, right? December 11 to 13, unless I made a mistake. Okay, so let me tell you what I'm looking for in this project, right? So for the first part, you need to log, and logging is not necessarily something simple, right? So let me point out a particular difficulty there. I mean, it's not a big difficulty, but something to be aware of. And if you're not aware of, you're going to influence the system. So here is the big issue in general, right? It's not obvious at all. When you measure, you could influence the system. And you could influence it in such a way that it runs in a different way than when you don't do the measuring. So here is a nightmare scenario, right? If you turn on the measuring, the system behaves, and it does the right stuff. You turn off the measuring, and it goes haywire. So why is that a nightmare scenario? Because the reason to have measuring in the first place is to figure out why the system doesn't work. But the system works when you have the measuring on, right? So why would that happen? Because depending on how you measure, you could, in fact, enforce a certain order of execution of things. Okay? So let me just point this out. And this is why you have to measure in a different way and organize the measurement in a different way, not to enforce an order. Right? So what I'm asking you to do is log. Logging means put information on an external resource that can be analyzed afterwards. Don't try to analyze at the same time, because then you're going to spend too much time on the analysis, the live analysis, and that will definitely change the way the program works. You will change the timings inside and whatnot. You have to do the smallest amount of effort possible with logging, to just log and nothing else. But here is the danger with the logging, okay? Suppose you have two actors, actor 1 and actor 2. You need to log. If all your actors or actors share logs, you're in fact influencing the way the actors work, because you're going to sequence the execution of the actors because I have to write in the log. So writing in a file, and this is something that all the programming languages have to do. Writing in the file has to be sequential. You have to enforce a certain order, because otherwise you're going to mess up the file, right? So in order to prevent mess-ups on the file, and by the way, this is where the end of line comes into play. So it turns out that writing to files in Unix systems, and to a large extent in Windows as well. And in Windows is a bigger disaster. Well, you could open the file multiple times in the same process, and you still need to be worried about this, right? So when you write in a file, the information is going to be propagated in the file or written in the file when you have multi-threading, right, based on what you write in a single write, in a single thing, right? If you write sequentially, you can, I mean, if you do your writes into multiple pieces, you can run in trouble because your writes get scrambled. But not only that, but when you write, you have to acquire some sort of lock, because the writing to the file, it's a single resource that needs to be protected, because otherwise you're going to get essentially a seg fault. You're destroying the library, right? The data structure of the library, which means if all the actors write into the same file, you're imposing something that you don't want there. You don't have the natural execution of the actors. You're now forcing them to stay in line to be able to write in the log. So what this basically suggests is the fact that it's essential that every actor gets its own log. Okay, this is where it starts to be fun. So you need one file per actor. If you don't do this, you will impose things that shouldn't be there. You turn the logging on and off, you get different behavior. Not good, right? The idea of logging is to capture as close as possible the actual behavior of the system. Okay? That means basically that you're going to end up with lots and lots of files that you have to put and patch the world together, right? So you have to figure out how you put them together. It's easy to just put the log, but I mean, now suddenly you have to deal with issues like global time versus local time and things of this sort, right? So put a lot of thinking into the logging. Don't just do something and say, yeah, that's my logging, because you're not going to get a good result for whatever you put on top of the logging. So this two-part project, in the first part, I'm asking you to come up with an elegant solution for the logging. And you have to be aware of these issues, because otherwise you do a really bad job there. In the second part is to take these massive files with the logs and do something interesting with them. So what's interesting? Well, interesting is, there are many kinds of interesting, and I'm open to lots of kinds of interesting. But some that I had in mind when I made the project are interesting visualization, some sort of graphs, some sort of things that show me the sequence in which the events happen. For example, if you took an electrical engineering class, right, you see those timing diagrams in which you I mean, we had some of them in the class in which arrows showing me at various moments in time how the action actually happened. Right? That might or might not be manageable, right? So when you have 10,000 actors, it's not clear at all that watching anything would work. So even for that, I mean, even for the visualization, you have to be aware of the fact that, I mean, I want you to be able to debug in this way with your tool, project number 3, let's say, which is kind of the more intense one. And if your tool doesn't know how to deal with 10,000 files, doesn't know how to survive selecting subparts of what you see and make some kind of, put some structure into the madness, I'm not going to be particularly happy. That's another thing. But other things are this kind of, I mean, the equivalent of assertions. So how do you know a system, I mean, how do you know in general that the program works correctly? Well, you could come up with constraints that have to be satisfied in various parts of the system or globally in the system. You're not used to global asserts usually, because you put asserts in a particular point in the program. You say, at this point in the program, this has to be true, otherwise I mess something up. Right? I mean, including things like, if I got an integer parameter, n is supposed to be positive, because otherwise, I mean, maybe it's the size of a vector, and if I got -1, what does that mean, right? So this is what the asserts are usually used for. But another thing that would be interesting, with or without visualization, would be to describe in some language properties that have to be true, and the system tells you when they are not true, and extracts some kind of a scenario when they are not true, or says, yes, it's true. So then it would be interesting to come up with mini languages, right, in which you describe things like a message like this is followed by a message like this. For example, imagine, this is a basic thing, right? If you have an actor that gets a message and has to respond to that message, but you could get more of this and more of this, but you want to make sure that every request is followed by a reply, one constraint is, oh yeah, is it the case that these messages are paired? But the question then is, how do you express that in some kind of a language? How do you enforce that? What kind of analysis you do on those things, right? Now, I don't expect you necessarily to produce super polished and complete solutions. I want you to give it a good go at this. But some of you will produce things that are actually very interesting and very useful. And I'm trying to get those kind of projects going, right? Of course, I expect all of you to have something interesting to show me by the time you demo this project, right? So because it's so open-ended, I don't even want you to submit the last project. You will show it to me in person in the exam period, unless you're an ed student when we make some kind of other arrangements, right? So you can do anything that doesn't even involve Scala, or I don't care. I mean, you have to do the logging in Scala because that's what we care about, but the analysis itself, the technology you use to do the visualization, it can be anything, right? So the problem would be running Scala to get good logs and then have some sort of tool that goes over the logs and shows me interesting things or automatically checks something or things of this sort. So you have to make up your mind what your strengths are, what you like, and what you're going to tackle for the part 2 of the project, right? I don't want a single kind of projects. I want variety. Now, you're going to get 2 benefits out of this. One of them is, at the end of the semester, you would have something interesting to show. And the other one is, hey, I not only came up with a good solution, but I came up with the right problem to solve. So I'm open to, hey, this would be the really cool thing to have. I identified the cool thing to have, and I build it, and here is the solution, right? This is why it's important to have the experience of all the other 3 projects and the frustration of all the other 3 projects to figure out what is it that you need to build. Keep in mind project 3. I mean, all of them, but project 3 especially. And ask yourself, what is the toy I would have liked to have to find bugs in project 3 faster, right? Or things that are even more complicated than that, because you still have uniformity in project 3. Everybody does the same thing, and the mistake kind of propagates uniformly. But I mean, even things like this, right? It would be nice to have some sort of a global asserts in which you say, fundamentally, everybody behaves in roughly the same way. So they have the same kind of average behavior. How would you express something like that? Right? Or super nice visualization, web-based or some other based, whatever skills you have, right? So you have amazing, I don't know, JavaScript skills and you know how to set up some kind of a web interface. Set up a web interface to see these things, right? If you're very good with some .NET this and .NET that, or some other tool or some other thing or whatever, use that to make something out of it. Now, this kind of tool building is essential for a successful new novel project. So if you end up in a group, right, somewhere in industry, that does something very fresh and very new, the key to success is the tool building, right? So this is something neglected by everybody. You say, hey, good software engineering, it's all about finding, you buy an expensive tool and you use the expensive tool to get your job done. Now that's true when it comes to AutoCAD on Verilog or whatnot, with this hardware design and some other issues, in which the tools have been, in fact, perfected for tens of years. But when it comes to this kind of things, right, for example, actors in Scala and so on, there are no tools. I mean, ACA people have some, but by the way, the really good stuff, it's only available for a lot of money. Is their enterprise product, right? So we're going to sell you an enterprise product. So don't just say, I'll buy ACA Enterprise and I'm going to use it to debug to your own, right? Building your own tools, it's a crucial skill that you need. You don't have the ability to build your own tools to build the main thing. You're not going to make as much progress as otherwise you will, right? Show me what tool you can build. First step, logging. Second step, what do you do with all those log entries, right? You can easily end up with many megabytes of logs in a good run, right? So, for example, 1 million lines in the global log, I'm sure you probably already reached it, right? With 10,000 guys that are aggressively communicating and doing things, you run it a couple of seconds and you end up with 1 million lines in the log. What do you do with 1 million lines in the log? Right? Having the information is nothing if you don't have a way to see what's happening, right? Now, this problem, it's so important that any kind of thinking that you do on this could probably be translated into very bold stuff you can do in other circumstances. I mean, this is literally what the hardware designers had to do. They had to invent these tools that help them, if you want, debug this kind of a very parallel, very aggressive systems. This is not something that normal computer scientists are used to. And now this is your chance because of the actors in Scala. So you're much closer to, if you want, hardware design. I'm even open to things like, hey, I figured out how to use a hardware design tool to do actor stuff, but it's probably not going to work because these actors are more flexible and right, they're not as controllable as the actual hardware thing. So just, I mean, amaze me with what you're going to pull off in there, right? Open-ended, it's both a great thing and a curse potentially, right? But literally, so your problem, so I want you to understand that the basic problem is the following. You have a complex system like the ones you wrote before, Project 1, Project 2, Project 3. You have to build tools and convince me that those are useful tools to, in fact, debug the programs you wrote. I will literally ask you to demo your tool on logs when you add the logging ability for the Project 1, 2, or 3, or whatever else you wrote, right? So you have to convince me that whatever is it that your project does, it's in fact useful. I mean, what I want is what happened, for example, last year, in which people got so excited that said, hey, we actually found bugs in the code that we thought was running well in the other projects. Hey, this kind of circumstance, right? We wrote this tool and we analyzed and we did this and hey, we realized that these 3 lines of code were wrong. That's the kind of stuff I want, right? Because the fact that it didn't crash before you submitted it doesn't mean it's good, right? So, okay? So is it kind of clear? So logging, it's far better defined, and to some extent is not as hard a project as the other projects. You just have to think a little bit, make sure you put the file per actor, because without this, you're really going to have a big problem on your hands. You're not measuring the right thing. The second part, much more open-ended, potentially a lot more work, right? Especially if you really want to do something neat and nice that you want to show to other employers. But the last project is by far the thing that will allow you to brag about and get great jobs and so on. right? So treat it in that way. So don't only necessarily think, yeah, did I do enough to get whatever the instructor wants for this class? Is this cool enough to talk to any guy that ever did distributed systems and to amaze them with what I have? Because if that's the case, I mean, you can show off any skill in that, right? And this is why I want you to capitalize on your strengths. So pull together all the skills you have and figure out what is it that you want to do for distributed debugging, which aspect. You don't have to do everything, just a good focus aspect of that, and that's going to be enough. Okay? Is it clear why the measuring can influence the execution? Now, this is something you're not usually told. And by the way, this happens everywhere. So when it comes to multi-threaded systems, the moment you give up the purely predictable sequential program, right? Even those are semi-predictable only because the timing of how fast or you can read things from the disk and so on might influence the program depending on what is it that you wrote. But if you write a normal program that's sequentially supposed to be deterministic, Intel and AMD swear that their machines are deterministic or at least look deterministic to you, right? So if you write a sequential program, then measurement, printfs, and other things you do or going step by step with the debugger or whatnot should not really influence the way the program runs. It's supposed to be deterministic, unless you're really measuring, for example, how much time a certain thing takes. And then, of course, any slowdown is going to change that. But the moment you have any kind of parallel execution, any measurement will influence the way the program runs. Right? So, for example, a particular frustration, if you take the database implementation class, you're going to have that. A particular frustration is if you have a multi-threaded program, and this is even basic stuff breaks down completely. It's beyond annoying. Okay, so let me explain. You have this multi-threaded program. Okay? And you want to do something very basic. You want to say, I need to go step by step with the debugger. Okay? But you see, there is no more step by step. You attach GDB, and this has probably happened to you if you try to do certain things, right? You attach GDB, and guess what that GDB will do? Will stop the whole program. So when you say stop, it will kind of stop somewhere. Kind of stop means each of these threads ends up in whatever place it ends up, okay? Even ask yourself the question, how do you actually stop a multi-threaded program? Literally, you have to go, and you have to go sequentially. You can't just say stop. There is no such thing as a system stop. There is no button that you can press unless you plug the power, okay? There is no button you can say everybody stop. There's no such thing. You have to go one by one and tell those guys to stop. And to stop, literally, you need to do some kind of a kernel system call to tell the kernel, stop that thread, okay? So even stopping has to go sequentially. There's no such thing as stop. Okay? So anyway, they ended up in whatever places. And you say, hey, I'll go step by step. Now, okay, first of all, GDB has to figure out step by step in which of these guys, right? Because of where you are in the program and whatever you're doing, whatever you put a breakpoint, for example. If you put a breakpoint, the system is supposed to stop. It will stop, kind of. You do a step here, right? Because of the user interface interaction, these guys whoop, are right here, right? Now, depending on what you did, literally, if you have a bug in your program, they can literally invalidate even what you're looking at next, because these guys run much faster. When you say go a step, GDB will go a step in this guy, not go a step in everybody. The GDB can't even go a step in everybody because of how heavyweight the mechanism is to go a step at a time, right? So suddenly, you're changing in a massive way the way the program runs. If you go step by step, for example, if this is the critical guy that influences in a bad way all the other guys, by slowing it down by many orders of magnitude because of the stepping one by one, you might not see any bug whatsoever. It's perfect. It's only bad when it runs on its own at full speed. But when you go slow with it, it's not bad because the other guys have the chance to go through regions that should have been locked and go safely because this guy doesn't interfere, right? To some extent, the same, you have to protect against the same thing. So now suddenly, what's much more important is to be able to measure things in parallel and analyze the measurement rather than try to do any of these step-by-step things, right? So distributed debuggers are, in this way, in the GDB sense, are far less useful than log analyzers, right? Now, even when you do printf, so you say, hey, I'm going to put lots of printfs, right? It's the same issue, by the way. The issue you have here with the logs is the same issue when you do C++ programming in a multi-threaded way. If you put printfs, because printf is thread safe, you sequence all the actions, right? While this guy is printing, everybody else is forced to wait, which means you're going to make them go in a synchronized fashion, which might make your program go better just because of the printf. So you print, everything goes well. You take the prints off, everything goes haywire. So what you do there, exactly the same thing you have to do with your actors. Everybody writes in a different file. Every thread has its own log, writes in a different log, you analyze the log. So whatever is it that you're doing for this project is not something that's good for Scala. It's something that potentially could be good for a lot of other things. And almost nobody is doing, because we are all into this step-by-step debugger mode, which doesn't work. Right? On a single machine, it doesn't work even when you have 4 processes or 4 threads or whatever. If you have a distributed system, it's hell on earth, basically. Right? So they have these systems with thousands of machines, tens of thousands of machines. And literally what they did is fault tolerance, which I'm about to talk about. You say, whatever, we'll never make it work properly. Let's just detect when it goes haywire and do some killing left and right to get rid of the bad guys. Right? As opposed to ever debugging this. I mean, people literally abandon projects because of the distributed debugging. You go at it a couple of months, and then you say, enough, it's enough. This will never work, right? Let's just give up. By the way, a fully distributed system, to a large extent, will solve these problems. Right? This is why, for example, database vendors, let me just point this out. I point this out in a much bigger way in the database implementation class. But this is one reason why you're going to see something that looks foolish. Namely, instead of, so imagine you have a machine with 32 cores. Again, remember, 32 cores, I mean, 16 cores, it's equal to $509, OK? I can tell you where you buy a chip. It's $509. Well, it can go to 1,000 if you want higher frequency, OK? So literally, if you have a server that does not have at least 32 cores, the cost of keeping the machine in the data center is going to be, for a year, is going to be higher than the cost of the hardware. Okay, just putting the machine in a proper air-conditioned room will cost you more than the server if you're not squeezing in at least 16 32 cores and a lot of memory. Right? So those skinny servers that have 2 cores and 4 gigs of RAM, right, they are not worth the electricity they are using, literally. Okay? So the moment you have a 32-core system, which you should if you have the smallest server you have, okay, it would be nice to have a real multi-threaded program there, not separate programs. But the danger with multi-threaded program is this kind of thing. If it runs haywire, you can never debug it. Now, this is the importance of the tool you're about to build, right? If you can't debug it, then you're in deep trouble. And you might apply a solution that's universal, but will rob you of performance. The solution is you're going to virtualize the machine and pretend it's 32 machines. Literally, at least you go from threads to processes. But possibly they go even further than that. Instead of threads to processes, you literally use virtualization techniques like VMware, and you literally run 32 operating systems on it. You have a base operating system that simulates another 32 operating systems on top of it, in which you partition the memory, partition the hard drives, partition everything. Right? That can't possibly be as good as using all the resources at the same time. I mean, it's obvious, right? You have a lot more flexibility if you can move anywhere you want on the 32 cores, on the large amount of memory and large amount of hard drive. But literally, a lot of the solutions out there right now are more like this than actual multi-threading because of the frustration people have with multi-threading, which basically means the following. If you do a good job when it comes to this debugging tool, you can allow people to increase performance by a significant factor, by transitioning from independent machines, even though you could run a 32-thread system versus 32 virtual machine system, right? I've seen situations in which I got a factor of 10 improvement. I mean, the overhead can actually be significant. It's not only the overhead. There is something else which we need to talk about, which is load balancing. It's related to fault tolerance, by the way. Right? It's related to redundancy and reliability issues that we talked before. And I mean, what's load balancing? Let me just mention this since I open up the topic. What's load balancing? I have many tasks that I need to run, or a big task that somehow I cut into subtasks. Load balancing, it's all about getting the large number of jobs and cutting it into pieces and give one piece to each of the machines to run. You've done it in your first project. Your first project was about load balancing, right? Was about getting a sequence of things that need to be done and distribute the work to multiple things. Now, I already forced you to come up with a good solution, by the way. But that's not the solution most people find. Because the solution mostly used is the following. I take the entire job. So let's say I have these 32 virtual machines. I take the entire job before I start. And some of you tried this, probably. If I take the entire job and I cut it in exactly 32 pieces that are exactly of the same size, and I run it, right? Then you would think, you say, hey, common sense dictates that they're going to finish at about the same time. That's absolutely not the case. Okay? You can do this in highly controlled environments. And what you're going to notice is then when you do this, is one of the 32 guys is at least twice as low as the average. At least. Okay? This is kind of the curse of load balancing. Let's call it that. Okay? So it's things that should work don't work. Now, why? It's an extremely complex system. Right? You can't know for sure what happens when this guy takes every portion. So what did you do in your first project? I essentially suggested to you, well, you had to find the right balance, right? You can go in the other extreme in which you cut it into too many pieces, and that's not good. But if you cut it just right, so you're not doing too much communication, you, in fact, have something I call automatic adaptive load balancing, which is much better, which consists in the following thing. Right? You cut it, let's say, into 3,000 pieces. Now, look what's going to happen. Each of these, by the way, it's not the case that one of the processors is going to be twice as slow. You run it again, and a completely different thread now is the lazy thread that finishes at last. It always, there is no rule to it. Okay? I've done this test, right? You run it, another guy is lazy. You run it, another guy is lazy. You run it, another guy is lazy. It's not a matter of find the lazy guy and give him less work. You cannot know which is the lazy guy. So if you cut it into more pieces, right, and you give a piece when somebody is done, then even if you have lazy guys, they have a blip on portions, right? Literally, if a guy is stuck here for 10 times more than any other guy, it doesn't matter because all the other guys are taking the work that this guy did. So this kind of size it into smaller pieces and do the load balancing tends to work much better. But for this kind of things, you need a very good distributed debugging because it's not possible to do if you pretend these are 32 machines. This is the point I'm trying to make. So literally the solution out there for almost anything that means distributed computation, which is now the primary reason you want to do a lot of these things, is cut the machine into slices. You have all your machines. You take all the work. You uniformly distribute the work to everybody, right? And then you say, oh, they all do the same amount of work, they should finish at the same amount of time. We need to talk about, for example, MapReduce. And in the first MapReduce paper, something amazing happened. I mean, it's about fault tolerance. I mean, they realized that if you run a computation on 1,000 machines, and the computation lasts for 20 minutes to an hour, you're guaranteed that at least one or two machines fail. Well, we need to talk about failure. So they noticed this, right? If you don't accommodate failures in computation, you never finish, literally. Because the probability that you're going to run without the machine failing if the computation lasts 20 minutes, an hour, it's about zero. I mean, you have to run forever. We can do a little bit of math to figure out how this actually goes, right? So what they did instead is build some fault tolerance, and then they basically said, hey, we improved the performance by a significant factor. I mean, even if they finish, some of them are going to be much slower than others. It's the same principle as this one. Right? Now, there is something interesting in here, even with this, with some of them much slower. Let me just point it out, and then we go back to fault tolerance. One possibility, which we do not talk at all about, is the following. If the computation is a pure computation, there's nothing preventing you from asking two threads to do the same computation, as long as you throw away all but one result. Okay? So then a particularly interesting technique is the following. But this requires good debugging, because you're not going to pull it off otherwise. Is somebody monitors these guys, and if you see they are too slow, you declare them faulty. We are going to talk about faults, but one of the faults is you're too slow, not necessarily that you're dead, you're too slow. And if you notice somebody is too slow, you can give the work to another guy, right? Now, if indeed you have one of these hiccups that does happen, right, then essentially the first guy that finishes, you're going to take the result, the other guy, whatever, finishes eventually and does something, and you go on with the computation, you finish the final computation even before that slow guy is done. Okay? It turns out that this improved performance in a MapReduce system with many, many cores by a factor of 10, because they noticed something weird. Okay? If you make a plot, if you do this perfect load balancing, if you make a plot and you look at the arrival time of the results of what seemingly it's supposed to be the same, right? You're going to have them nicely clustered here and then a couple of guys that are way, way, way over, right? The running time of the entire thing is this, guys, not the average. You can be amazing on average and disastrous in terms of computational time, overall computational time. So by essentially monitoring who finishes where and determining some kind of an average running time and asking somebody else who finished their job to do the job of the other guy, you could actually have a total running time about here and not about here. Right? So these are called outliers. Now, why outliers happen, we don't know, we don't fully understand. Right? Because it's a very, very complex system. I mean, why that? I mean, a lot of things can happen. For example, the operating system decided to do something in parallel with your process, and it hiccuped. Or it detected some failure on the hard drive and couldn't read the block. Or, I mean, a million things that can happen. When you have enough systems, right, the probability that something happens in that system goes up significantly. We can do some math, and that's what some probabilistic analysis on fault tolerance is all about. So one way to improve system performance is by declaring things to be faulty when they are slow and not only when they fail. They literally had failures, and then they not only had to they realized something magical, that if you declare somebody slow to be dead and do something about the failure, not only that you solve the problem that the computation was not finishing before, but you run much faster because you're masking these outliers as well, not only the faulty guys. You mask the slow guys, not only the truly faulty guys. Right? You have to be aware of this, of these things. You have to program for them. In actor model, it's kind of straightforward to do this. Right? I mean, for example, project 1, what was that main guy doing? I mean, he has no better thing to do than monitor what the other guys are doing, right? Because he's not doing anything. Especially if you have a sizable amount of work for each of the guys, right? The main guy has the best job in the world. I mean, he's doing nothing, almost. So make the guy monitor, or make another actor that monitors. Now, something that, and this is why this project is going to be very important. This is why I'm wasting so much time on this, or maybe spending so much time on this. We do a lot of projects. I notice this over and over. We do a lot, build systems, build projects, and so on, but none of them are built with self-monitoring in mind. To a large extent, turning on and on this kind of logging and having log analyzers it's a form of self-monitoring. You can actually do bigger tricks, and I want you to even investigate this. For example, one of them would be, instead of logging to a file, stream the logs to some remote machine or a remote process, and have that guy not only store the logs, but do live analysis. That would be a form of self-monitoring. I mean, you help somebody monitor you. Right? It's basically right there in the self-monitoring. Well, actually, in the database engine that we are building, we have true self-monitoring in which the system is looking at. I mean, one actor is just watching things and not only sending logs to another place, but monitoring things a little bit. Right? So once you build mechanisms to do self-monitoring, sky's the limit with how sophisticated you can get and how much benefit you get out of it. Right? So instead of designing systems that never fail, if you design systems that do self-monitoring and have good things they are measuring and good things they are keeping track of, you can detect a lot of problems, and by building fault tolerance into your own system, for example, I mean, you detect that an actor does weird stuff, just kill it, start another one. But how do you detect? You have the same issues that we need to talk about in distributed systems when you even do a single 32-core machine system. Right? You have somehow somebody trampled over the state of one of these sectors, you're much better off by essentially finding that, right? But think even about this issue is, how would you measure the average behavior, and how would you detect the guys that are way over the average behavior? Maybe it's not so hard, right? First project again. All you need to do is remember at what time you ask any of those guys to run. You're measuring when the results come back, and you can maintain some kind of an average, and you can go over your data structure and say, hey, guy number 3, what's wrong with guy number 3? He's 5 standard deviations away when it comes to average behavior, and these guys. Because in Scala, you can even kill actors. You say, something is wrong there. Kill that guy. Start another one. That might, in fact, make things work much faster. Right? So these kind of outliers will kill the performance. We just kill the performance. Right? So even if you want performance and nothing else, that's a much, much better solution. Okay? So keep these things in mind when you do the fourth project. Don't only think about the Scala situation. Think about this kind of situation in general. Ability to log. So keep in mind that it's not only logging, it's what you log. So ask yourself the question, what should I log? Right? Now, of course, you could log everything, but then that has a nasty side effect. You're going to spend all your time logging, right? So logging itself, it's an art. What do you log? What do you put in the log? What's useful, what's not useful, right? So ask yourself those questions, and when you come and show me, especially the final project, hey, convince me you logged the right thing, right? So this is not only a project in which you go through a checklist and say, I've done this. This is a project in which you have to ask hard questions about how do I do it to get that good tool at the end of it, right? Ideal situation would be you get something so good, a little bit more work on top of this because you're not going to finish, a little bit more work on top of this, and it can be used potentially in production by your team when you go and do distributed things, and everybody does distributed things right now, right? So that's what I want you to keep in mind. This is a toy I could further extend when I join some sort of a group in a company to help them with the madness, because people are already going insane with the distributed debugging, I can tell you, right? It's a lot of sleepless nights, many of them. And of course, the boss says, what are you talking about? I'm sure it's a simple bug, go find it. There is no way to know when you find it. This is what I want you to understand. You already bumped into some of this potentially, but you're definitely going to bump if you take the database class, right? See, when it comes to bugs, you can't tell for sure how much time you need to find it. If I ask you how much time do you need to write a certain portion of the code, you can come up with some estimate. I'll multiply it by a factor of 3 because people tend to underestimate by at least a factor of 3 to 5 the time it takes to do something like code writing, and I get some sort of an estimate. But when it comes to a bug, it can be anything from 10 minutes to never find it. Right? So this is why these tools are important. So let's tab on some of these high-level fault tolerance issues, but they are tied with a lot of other things. Right? So logging, to a large extent, it's about potentially finding faults of a different kind. The log analysis will find some sort of faults, because otherwise, why are you logging? Just to count how aggressive the system is? That's interesting in itself. You can log to assess performance. You can log to find bugs. You can do both at the same time. All right? So profiling, logging can be used for profiling as well. Okay. Okay, so let's do some of this thing. Okay, so we talked about logging last time as well. Let me just mention some of the high-level notions from here, right? So fault tolerant, it's all about masking failures. It's not about not having failures. Fault tolerance means mask failures. If you assume that you're going to design systems that don't fail, you might as well give up engineering altogether, right? No such thing. The only things that don't fail are mathematical proofs, and even those, you can prove that certain things can't be proved, so then here goes your non-failing mode even for math, right? So the fault tolerance, it's all about availability, reliability, safety, and maintainability. Okay, so what this means is availability means even if things go up and down in the internal system, the system can still function. That's all about finding the fault and correcting the fault as you go along. Okay? You just have to remember that the thing you want is that the users perceive the system as still running, not necessarily that some subcomponents run without failure, right? Including things like if you have the ability, for example, to restart your program in a second, then detecting when the program went haywire and taking it down and up again in a second, that might be a much more acceptable solution than trying to never let the program die. And then if you have some kind of a watchdog, some of you mentioned the term watchdog last time. If you have some kind of a program that watches another program and simply kills it and brings it up again when it died, if that does not lose information or things like that, that might be a more than acceptable solution. The users will never know that you take down the process and put it up again. It's the same thing as rebooting the machine, right? I mean, availability and reliability are essentially tied together, right? So it's just different shades of the same thing. Now, safety has more to do with potential things related to access control and so on. But, I mean, depends on what the fault tolerance system is doing, right? And maintainability, okay, this is kind of interesting because if you're trying to write code that doesn't fail, your code will become very complicated, okay? So, and that's something that's really, really, really bad. So one way to keep things simple. So the secret when it comes to software development of any kind, I mean, I know some of you were in industry and so on. The secret with anything we do, actually forget about software development, is to figure out what the simple solution is. Okay? So in certain circumstances, I needed many years to find the simple solution. Okay? If you don't have a simple solution, you're in for a big trouble. The point I'm trying to make is fault tolerance technique, fault detection and fault correction, might provide a much simpler solution rather than a non-faulty system in the first place. Writing a program that has no bugs, it's much harder than writing a system that can monitor, detect if there is a problem, and find some way to correct it, as in takes the system down, put it back up. That might be much easier to do and get to run reliably than a system that, in fact, has no bugs. Okay, we know that, for example, from operating systems, where you can't afford to take it down and put it back up. Right? If you could safely purge part of the state, clean it up, and build it again, that's a much better mechanism to get things fixed and running and have a simple solution than to try not to have any kind of a mistake in that code. Also keep in mind that you cannot control all the mistakes because some of them are beyond your control. They're hardware related. You will always have a little bit of hardware hiccup. Not to mention that you're not paying only for your mistakes. You're paying for the mistakes of everybody. That means your teammates, your company, if they wrote part of the libraries, the library provider, whoever wrote libraries and things, the operating system guys, the hardware guys, everybody. And the cosmic rays, right, that might do things to stuff. Or, right, simply somebody forgot to turn on the AC, right? Or the AC faulty might mean your program is faulty because the temperature raises in the room where your server is, literally. I mean, you can't prevent all problems in the world. So by monitoring, you can then have a more general solution of what these things are. So this is why literally fault tolerance should be taught in a basic programming class. But I know very few people that write programs that monitor themselves and try to kill parts of it and do them again. But with actors, that's in fact a reality, right? So maintainability, you might have a much easier to maintain system if you in fact detect faults and correct faults, especially if you pair them up with nice visualization of what actually happened there. So when it comes to this, for example, you could use the log not only to find bugs, but to, in fact, do failure detection. If you stream the logs to a separate component that tries to analyze what goes on, that component might say, hey, one of your workers is ran amok, is not doing enough work. Kill it, start another one. Probably something is bad with it, right? And that might actually solve a lot of problems that you have with your own program. Right? So lots of possibilities open up if you do this, especially if you find a good, tight solution that does not influence too much how the system runs. Right? So we talked about kinds of failure. So I want to briefly mention them. Again, the discussion in the textbook is a little bit more systematic. Right? So crash failure, most obvious one, the system went down completely. Almost never happens now, by the way. Well, they noticed when they had 10,000 machines, for example, in that distributed computation, that literally machines were rebooting. At least in 1 hour, in 1 in 10,000 machines, at least one of them was hiccuping. Now, this is a much higher failure rate usually than you would have in a normal machine, and that's due to the fact that they were pushing the system to the limit and they overcrowded those machines. I mean, even cooling all the stuff there is kind of problematic. I don't know if you know, but Google has patents on how to cool servers. I saw a nice documentary in which they had this super, super nifty setup for cooling. And you have problems in a data center that you can't believe are even problems, right? You buy a computer, you put it under your desk or on your desk and say, yeah, that's it. But not when you crowd them up, right? So it's a very different story. By the way, just to give you an idea, only the air conditioning unit that we use in one room in the department to cool off all the servers that you put in that room, it's about $100,000. Right? So when you think about the cost of a machine, it's not only the cost of the hardware, it's the cost of electricity, the cost of the cooling, cost of the people that have to watch over it, the building, all that stuff. Omission failure, right? One thing we did not discuss too much is you have all these messages going around when you do distributed computation or even when you do it on a single machine. Things can get lost, right? If they get lost, that's in fact an omission failure, right? So we talked about all of those protocols and we say, oh, hey, you wait for a message from all of these guys and you do something. What if a message never comes? Well, you need a protocol that accommodates this kind of message loss. Now, remember the difference between TCP and UDP? TCP is watching for those message losses and will insist on guaranteeing the delivery of the messages, or in fact giving you a complete failure message saying, hey, the connection timed out, it did something, and so on, right? So the moment you use TCP, you have at least some base, which is you're not going to lose messages. Why? Because TCP is looking for you, but potentially the performance goes down, maybe, right? So omission failure. So when you design a system that's fault tolerant, you have to, in fact, specify which kind of failures you can accommodate. Right? And to compensate for the failures you cannot accommodate, you might use services that guarantee that thing. But you guarantee. So what does it, how do you think TCP guarantees message delivery? Or, right? By moving the failure in the protocol, in the TCP. It's not that the failure is not there. It's a different component takes care of it. Right? So TCP will, in fact, mask failures. It gives you the messages only when they are nice and clean and in order. But they could have failed, and TCP detected it. And if it detected it and found the corrective measure, it corrected it. If it cannot do any of those things, we'll say the connection is down, even if partially it wasn't completely down, right? So there's no such thing as things that don't fail. There is only pushing down the failure detection and the failure kind of recovery in subcomponents. That's what TCP does for you. So when you use a library, right, that provides a high-level surface, in fact, it does a lot of failure masking. That happens all the time, even with other things that you don't even realize, right? For example, you open a file and you do a read on the file. In fact, there is fault tolerance in the operating system, and there is fault tolerance in the library, knowing that things just like to be hiccupy, right? So for example, when it comes to physical devices, you ask a hard drive to do something for you. It might just not do it. You might say, wait a second. Well, I mean, lots of things can happen with a hard drive, right? I mean, the hard drive itself might have monitored itself and realized that something is completely haywire, reboot completely. Here goes 300 milliseconds. This is why things can go fast and then suddenly they go slow, because one hard drive realized, like, hey, something is completely messed up. Let me reboot, right? Reboots, forgot about your request. Then what's going to happen is, this is the difference between the older version of the operating system and the newer versions, right, or different operating system, right, is the OS literally will monitor, detect faults, and cover faults. This is why things get slower, because the OS said, hey, this hard drive did not, I mean, you know that the average behavior is it has to come back in, I don't know, 10 milliseconds. 20 milliseconds later, it's still not back. Something is messed up with this. You can even start a hardware reset. You say, something is very wrong with this guy. It wasn't working properly. This is literally what the OS will do, Linux will do. Send a reset signal, reset the whole thing, maybe it come back. You do this 10 times, it still doesn't come back. Then you bug the user and say, hey, I can't mask the failures anymore. So a lot of what goes on in general, and this is what you would have to do when you design a system that has fault tolerance in it. You need to mask failures up to the point where you can't hide them anymore and you have to expose global failures, right? TCP does that for you, OS does that for you. You have to do it for other people. So usually, as a programmer, as a designer for a high-level application, you don't want to know about failures. It's a, hey, it's like a boss that's a very high-level boss. You don't tell me that you failed. Find a way to fix it. Just go, right? It's the same thing here. Find a way to fix it. Fix it. You come to me only when it's unfixable, right? But when you're designing protocols, depending on what you build on, so you always have to ask hard questions about, is the library that I'm building on providing some of this fault tolerance facility? And then you put your own fault tolerance on top of the fault tolerance, because usually you need multiple levels of such things. So TCP will allow fault tolerance at the level of message delivery and message losses for point-to-point connections, but will not do such a thing when it comes to a distributed computation. So a lot of what we talked about in class was about how to build upon the reliability of TCP and extend the reliability to much higher level kind of reliability, right, that group communication and so on, right? So that you can mask. You see, from the point of view of the user, for example, I'm a Gmail user, which I am. I don't care about all the almost 1 million servers that Google has. I don't care about the fact that one of the servers died while it served my mail, right? Now, if it's a little bit hiccupy, I'll do a couple of refreshes. But what I do expect is when I do a refresh, somebody picks up the job and does it. I mean, don't, right? I want Google to look to me like a nice, super stable machine that does what I want and nothing else. I don't even want to think about it as many, many little machines, for example, 1 million machines. I just want to think that it's this nice machine that's dedicated only to me and that magically does all the work. This is what fault tolerance is all about. This is what you have to design for when you're doing your own things, right? We're going to talk about some of the techniques, but we already bumped into them. A lot of those total multicasts and all those building blocks can be used to build some sort of fault tolerance, right? So we are going to spend the full next week on fault tolerance. It's that important. I'm going to go through lots of details, lots of scenarios, lots of things, and talk about particular strategies, and talk about limitations, right? This is something that it's not ever talked about, because there are some fundamental limitations when it comes to what extent can you mask failures. I mean, a fundamental question, which I'm not going to address at all now because time is almost up, is can you always mask failures? And it turns out that the answer is no, unless you constrain the building blocks that you have in a certain way, which it's unrealistic. I mean, eventually you can build something that has to propagate the failure and has to expose the failure. Okay, all right. So I'll see you Tuesday. We're going to have a quiz covering the stuff we talked about, high-level things, and focus on the project, right? And start working on phase 2 much earlier than November 23rd, midnight, when the project is due.